So, all right, welcome to week 7 of the live session which we are having, and today we are going to discuss OFDM, that is orthogonal frequency division multiplexing, and we'll see the comb type OFDM. We'll see OFDM, its working, why it is so powerful, and how it is mitigating the uh, uh, so in the previous week, we saw the channel equalization in time domain, which was a zero forcing technique. And today we are going to see the OFDM, which is used to perform channel equalization in the frequency domain, right? And we will see how it is much better than the uh, time domain technique which we used, and why it is so powerful, and it is used as a base of 4G LTE systems. Right, so the 4G LTE systems has its base physical layer method is the OFDM, right? So we will see how it is, and so let us start. So OFDM overcomes the symbol interference with a very low complexity as compared to the zero forcing method, which we saw in the previous week, which was a time domain technique. And we will see the a very brief working of the OFDM, how the OFDM protocol works. So let us consider that the following time frequency domain symbols are to be transmitted. Now in OFDM we are going to discuss two domains. So we have the time domain, and we have a frequency domain. So what is the time domain? What is the frequency domain? So you can just so for now you can just assume that currently we are in time domain. So we are shifting the entire space, right, which is using the Fourier transform to another domain, which is the frequency domain, right? So we'll see how it is advantageous, why changing the domain is advantageous, and we'll see that, and how this interchanging of domain takes place, right? We'll see that also. So assume that initially you have, so how is our bandwidth? So in OFDM, we have the time and frequency. This is called a resource block. It's kind of a grid. So you have the frequencies, and these are subcarriers F1, F2, so on, Fn. Similarly, you have the time slots, say TM and so on. And this is called a resource block. The resource block is a time and frequency both are involved in a resource block. And uh, so say that the frequency domain symbols which we want to load on the subcarriers, say they are represented as x0, x1, x2, and x3. So currently we are having n equal to 4, where n is my number of subcarriers. Okay. So in general, it is represented as XL, which so XL represents the symbol which has to be loaded onto subcarriers. It can be real or it can be complex. So what is the meaning of a complex symbol again, right? So if it is complex, that means it is of the form a e to the power j theta. So this is of the form a cos theta plus j times a sin theta, right? So if you consider the space, you have the real space, you have the imaginary space, and this is how we represent. So this is my a and this is my theta, right? So this is how we represent the symbol in the space, right? Now if we want to convert the frequency domain to the time domain, then we use something which is called the inverse Fourier transform, right? And if you want to convert time to frequency domain, then it is the Fourier transform, right? So if you want to convert frequency, right, so let me just write it in arrow, it's not clear. So from frequency domain to time domain, we'll use the inverse DFT, and time to frequency is DFT. Now, you should know this. In fact, just a minute. Looks like I don't have space. Problem. So just to recollect, we have four. So we have the Fourier series, right? We have the Fourier series. Then we have the continuous Fourier transform, right? Then we have this is the continuous time Fourier transform. Similarly, we have the discrete time Fourier transform. And finally, we have the discrete Fourier transform. So this is the basic signal systems, and you should know this, right? If you do not know this, so and when you have the discrete Fourier transform, right? So here our time domain is discretized as well as my angular domain is also discretized, right? And uh, discrete Fourier transform has a complexity of I think n square, and so a much efficient way of performing the DFT is the fast Fourier transform, or the FFT, and this has a complexity of n log n, right? And please mute yourself, Doctor. See if I can mute. Right. So to overcome the, so discrete Fourier transform is a very uh, inefficient process, right? So you can do a very simple homework possibly in your home. You just take any image. OK, take an image, say 252 by 252 pixel image, right? And you try to perform the DFT on it, and it's a direct MATLAB function. It's a direct MATLAB function, and if you try to perform the DFT on an image, you will see that as the size of your image increases, the time required by your system, even if it is a very good high-end system, it takes a lot of time as compared to the FFT. Of course, the FFT, so as compared to DFT, FFT will not give you that good the frequency resolution, but still, to cut on the time complexity is pretty important in computer applications, and that is why fast Fourier transform is preferred. So in this course, we will be using DFT and FFT interchangeably, right? So don't get confused. So if we say that the frequency domain symbols are converted to time domain symbols through IFFT or IDFT. So let's not go into whether and in mathematics we'll be basically showing the IDFT only, and similarly DFT. So don't get confused that we have to perform IFFT, then why IDFT is being used. So the main point is that you have to convert the frequency domain to time domain, and we have to use the inverse discrete Fourier transform for that. And say initially we have the frequency domain symbols as capital X 0, 1, 2, 3. And remember that, in frequency domain, we will be indexing using L. Okay, in frequency domain, we'll index using L, and in time domain, we will be indexing the symbols with K and small x, right? So, and say we obtain in time domain small x 0, 1, 2, 3, and the IDFT formula is given in, say, this is my equation 1. So xk is 1 by 4. So in general, it is 1 by n. Summation L is 0 to n minus 1 xl e to the power j by kl by n. Okay, so we'll come to this when we'll okay, this is 2 pi. So when we'll solve some problems, we'll use this formula a lot. Now, once we have the time domain, the symbols in time domain. So when we transmit them at the receiver end, what we have to do is that we need to take the cyclic prefix. Why do we take cyclic prefix? So if we are doing, say, a time domain equalization, then as we saw in the previous week, we need to take the cyclic prefix so that the cyclic prefix gets corrupted with the intersymbol interference. And so even if my block which contains cyclic prefix gets corrupted, the actual message does not get corrupted and only the prefix gets corrupted. So that is the idea behind cyclic prefix. And how much cyclic prefix we want to add in the uh, how much symbols we want to prefix our block, that depends on the number of channel taps. All right, and say now this is my block which has to be transmitted across my ISI channel, right? So ISI comes with multipath, and say this is our signal model. So we are having two taps, H0 and H1, as we discussed in the last week. And now if you see at the receiver, the symbols which you are receiving is actually a circular convolution, right? They are you need to perform circular convolution so that you can receive the symbols, and then you need to then perform the zero forcing again, which is a very complex process. So what do we do? Right. So if you transmit symbols in time domain, so first thing is you need to perform circular convolution, right? And then when you receive the symbols in the receiver, you need to then perform zero forcing, which again is not very accurate because you are trying to approximate, the taps which you don't need, the equalizer taps you don't need to zero, and that is a pretty complex time complexity increases. So what we do is that rather than going through this cumbersome circular convolution and then time domain zero forcing method, we are going to bypass this by performing the FFT or the DFT and convert the time domain symbols into the frequency domain symbols. And now if we convert the time domain symbols to frequency domain, right? Then what happens is that in that case, you will be receiving YL is HL times XL plus VL. So this is in the frequency domain which you are receiving. And if you see that in time domain, we had YK, if you remember, was H0, XK plus H1 XK minus 1 plus VK, right? This was in the time domain. So what you are seeing is that when we use the transform to convert the symbols from time domain to frequency domain, now my signal model. So this is the new signal model. The new signal model is free from ISI in the new frequency domain, right? So this is why the the Fourier transform is so powerful, that we were facing this problem of ISI circular convolution in the time domain, but we don't need to do these things in the frequency domain, right? So there is no ISI on a subcarrier, and this is the formula of DFT. So let's not bother about the formulas right now. So when we'll solve the numericals, we'll use these formulas. So essentially what we are saying that is in the frequency domain, we have that y of 0 is h0 x0 plus v0. Similarly, y1 is so this is following the the general formula which we have, that is h x plus v, right? Whereas in the time domain, we had yk is h circular convolution x plus v, right? So this is what we were getting. And this, so plus circular convolution plus ISI, right? So we had both these problems, and in the frequency domain, we are mitigating both these problems, and that is why the OFDM is very, a powerful technique in the physical layer protocol, as a physical layer protocol, right? Now, if we try to represent in the matrix notation, we have the y vector, we have the pilot vector, this is our h vector, and similarly we have the v vector, right? So y is x times h plus v, and again the channel estimation is this is the least squares formulation, which we discussed possibly a couple of weeks ago. And how will you solve this? So this is again our the pseudo inverse technique which we have. So x Hermitian, x inverse, x Hermitian y. And why have we taken Hermitian? Because x can x can contain complex values, right? So why will x contains complex values? So again, our x can be of the form a e to the power j theta, where we have the real part, the imaginary part, right? And a e j theta is basically you have some a with some angle theta, right? And so this will be a cos theta plus j a sine theta, right? So this is what we have. Now we have the pilot matrix, right? So what is x? X is my pilot matrix, right? And we observe that so we are discussing this is in the frequency domain, right? This is in the frequency domain. This is not in the time domain. So remember in time domain how our the pilot sorry, the channel matrix in S domain used to be circular convolution. So if you just remember in the last week it was some h0 h1 0 0 0 h0 h1 0, right? So it was a circularly convoluted matrix which you are getting, right? So, but here what we are seeing is that the pilot matrix in the frequency domain is a diagonal matrix, right? And if you have a diagonal matrix, then it is invertible. That is, its inverse exists, right? The matrix inverse exists. And since the matrix inverse exists, and we use the property of the invertible matrix, that is x Hermitian x inverse is x inverse x Hermitian inverse. So if we use this, we get that h hat, that is my channel estimate, actually is x inverse y, right? So what we are getting is that h hat is simply x inverse y, right? That's it, right? Now, if what is x inverse? So for any diagonal matrix, x inverse will always be the just simply the inverse of all the elements, that is its diagonal elements, that is 1 upon that element, right? So this is the multiplicative inverse, right? So each element is the multiplicative inverse uh, of the diagonal element. and this is the property for any diagonal matrix, right, of any size. So if you have A0, 0, B, and if you take its inverse, so you will be having 1 by A0, 0, 1 by B, right? You can just check it with the cofactor method, right? And this is what we'll get. So what we say is that now my channel estimate is essentially, so H0 is Y0 over X0. Similarly, H1 is Y1 by X1, H hat 2 is Y2 by X2, H hat 3 is Y3 by X3. And note that we are all talking in the frequency domain, right? We are all talking in the frequency domain. This is not in time domain. And if you want to see what happens in time domain, then it will be a much more complicated analysis in the time domain. Right. Now what you can do is, if you want to now reconvert the frequency domain symbols into time domain symbols, then you can again use the inverse DFT or inverse FFT, and you can so this is my time domain estimate which we get, right? So what we are essentially doing, it's like without entering into the congested city, we are bypassing the city through a ring road, something like that, right? So right. So another topic which we have to discuss is the comb type pilot estimation. Now, what is the comb type pilot estimation? Now, this is a different scheme for the OFDM channel estimation. So say again, you have still the signal model, which contains the the multipath. So H0 and H1, you still have the two-tap signal model, right? And N is 4, that is we have the 4 subcarrier and two-tap ISI channel. And just remember that to perform the FFT or the DFT, we need to bring the matrix sizes to the same size, right? So we need to do zero padding for that. So zero padding is very essential. So since we have only L is 2 and my N is 4, that is why 2 zeros have to be padded behind our channel matrix. So just remember this is in my time domain. Right. So now we need to convert the time domain to the frequency domain, and we will be using the DFT process for that. And so capital H represents my symbols in the frequency domain, right? And how will we do that? So capital H of L. So this is my DFT equation which I have written. Okay. Now, when you will be solving this, you will be getting these 4 equations. So H0 is in time domain, it is H0 plus H1. Similarly, in frequency domain, H1 is H0 minus J of H1. H2 will be H0 minus H1, and similarly H3 will be H0 plus J of H1. So now what we have 4 equations, and we have only 2 unknowns, that is H0 and H1, right? So right. So in the comb type estimation, in the comb type of DM, what we do is that we actually have the information bearing symbols as say X0 and X2, and the pilot symbols are say X1 and X3. So rather than having 4 data symbols or 4 pilot symbols, we are interleaving the data symbols and the pilot symbols, and that is why it is kind of a comb structure, and that is why it is called comb type transmission. Right. All right. So now what we need, only need 2 channel estimates. All right. We only need 2 channel estimates. So Y1 will be H1 X1 plus V1. Similarly, Y3 is H3 X3 plus V3. So we need only Y1 and Y3. Why? Because Y1 and Y3 are my pilot symbols. That is what say currently we need, and we'll see that how only through knowing H1 and H3 we can compute H0 and H2, right? So we are saving on the bandwidth, and we'll see how we are doing that. So now our matrix model has significantly reduced. So earlier we were having a 4x4 palette matrix. Now we have a 2x2 palette matrix, right? And H hat is still X inverse Y as we saw earlier, right? This is still the uh, so using the invertible property which we had, right? And so what we'll get is that H hat 1 and H hat 3 is Y1 over X1 and Y3 over X3, right? And so now we had the system of equations which we saw above, and we use these two equations H hat 1 and H hat 3, right? And we solved 2 and 4. So if you solve 2 and 4, we'll get that H0 and H1. This is in terms of, if you see, H hat 1 and H hat 3, right? And if we put this value of H0 and H1 back in equation 1 and 4, because these two are still left to be computed. So we'll get the values. So just note that H hat 2 and H hat 3 are 0, right? Why? This is because of zero padding. So if you remember our what we had, H hat 0, H hat 1, H hat 2, and H hat 3, right? And this was 0, this was also 0, right? We had to do zero padding so that the FFT or the DFT can be computed. But note, so these are 0 in the time domain, okay? But if any variable is 0 in the time domain, it does not mean that it will be 0 in the frequency domain also, right? So that is why in the frequency domain it is not necessarily 0, right? So now only with two pilots, that is L is 2, we can estimate all the 4 channel coefficients, and that is why this comb type transmission improves the bandwidth efficiency of my system. So in summary, equalization, right? Equalization. Why does equalization happen? This is because of multipath, because of which ISI happens, which is inter-symbol interference. And we saw two ways how to deal with this ISI. So in the time domain, we saw the zero forcing, right? The zero forcing is pretty complex because it involves circular convolution in the time domain, and then it also has an approximation value only. If you just remember that we used to compute the projection matrix and all that, so it used to give an approximate value, right? And in the frequency domain, we saw the OFDM, and and as compared to the circular convolution, this is very less complex, right? And ISI is mitigated in the frequency domain itself, right? So there is no ISI which is not coming. So my YL is XL HL plus VL, right, directly, and I am not getting the ISI which I used to get in the time domain, so I don't have to do any zero forcing, and it improves bandwidth. How? If you use the comb type transmission, then you only need two pilots and you can estimate all the 4 channel coefficients as compared to the time domain strategy, right? So this is the a quick and brief summary. And now, any doubts in what we have discussed? No doubts. Okay. So now we'll go to solving some problems. So yeah. So what is the advantage of the comb type channel estimation? Right. So what is the advantage? Anyone would like to answer? Yeah, please go ahead.
Decreasing number of pilot symbols.
Decrease in number of pilot symbols. Okay. Someone else also wanted to say. You can also contribute. Yeah. Complexity of estimation. Decrease in complexity of estimation. Right. Right. So actually, so I would say that there is, so complexity of estimation is not actually decreasing by the the comb type transmission because so complexity decreases. So we have the the time domain which is zero forcing, right? And in the frequency domain we have the OFDM as well as the comb type transmission, right? These are the three strategies which we saw. So yes, as compared to zero forcing, certainly the complexity decreases, right? So the complexity, it will decrease in both the cases. It will decrease, right? Because both are using DFT and IDFT, right? But here it is as advantage of CTP over OFDM, right? CTP or OFDM. So the answer is that there is a decrease in number of pilot symbols, or you can also say that there is an improvement in bandwidth, right? Improvement in the bandwidth or the the frequency spectrum efficiency is improving, right? So that is the correct answer, right? So who I think Meha Goel said that decrease in pilot symbol. So good. So it's the correct answer. We'll move ahead. So right. So the minimum number of pilot symbols required for a comb type estimation. So anyone would like to answer this? Go ahead. Try anyone.
Number of channel taps L.
No channel twice. All right. We have got one answer. Anyone else? Some other answer? Oh. So right. So again, you are correct. The minimum number of pilot symbols required is the number of channel taps. Right. Okay. If anyone is having confusion, you can just ask anytime. So consider an given 4 subcarrier OFDM system, and we are using the CTP channel estimation and the symbols loaded onto the subcarrier. So this is in the frequency domain. All right, just note that. And then the pilot subcarriers are given as L is 2 and 3. So the corresponding received symbols in time domain. So now see so the receiver symbols are given in time domain, the transmitted symbols are given in frequency domain as in the question. And we are given that at each subcarrier we have a variance of -3 dB, and consider the frequency selective channel H0, H1, L is 2, and the length of cyclic with minimum required, that is 1, right? So cyclic prefix is 1. And what is the transmitted block, right? So let's solve this. So we need in time domain what are the samples which I'm transmitting, right? So we basically need xk, which is given as 1 by n. So n is 4, summation L is 0 to n minus 1, that is 3, x of L e to the power j 2 pi k L by 4, right? So this is my formula. What formula is this? This is the IDFT, inverse discrete Fourier transform, right? So let us just solve this. So what we have, right? So let's first solve for k0. Right? So what we'll have, x0 is 1 over 4 x0 plus x1 plus x2 plus x3. Is anyone having any doubt why at k0 x0 is written like this? If anyone has any doubt, just feel free to ask. Okay. So how did this come? So this is because e to the power j 2 pi k times L is 0, right? Since k is 0, so k into L is again 0 and by 4. So this entire exponent term is 1, right? E to the power 0 is 1 and that is why we only have x0 plus x1 plus x2 plus x3. Right? Okay. So this will be 1 by 4 and we are just going to add all the x's. So we have -1 plus 2j minus j plus 3, right? And this is 1 by 4, 2 plus j, right? So since we have some space less, so I need to open a note. Just a minute. Okay. Which one is this? This is sequential estimation. Just a minute. Just write at the end of this. Right. Right. So another just a small concept. So just remember that when we have the coordinate system and while solving the numericals, so just again remember this is my real axis, which is the sine axis. Sorry, this is the cos axis, which is real, and the imaginary axis is my sine axis, right? And on and if you have, say this is 1, right? So any point will be cos theta, say this is theta plus j sine theta, right? And one more thing possibly which you can know that, let's take another color. So if this is say 0, then you have pi by 2, right? Then you have pi, then you have 3 pi by 2, right? Then you have 4 pi by 2. What is 4 pi by 2? It is 2 pi, right? Then you have 5 pi by 2. Then you have 6 pi by 2. What is 6 pi by 2? It is 3 pi. Then 7 pi by 2, right? Then 8 pi by 2. What is 8 pi by 2? It is 4 pi, right? So if you just see which degree is falling on which axis, and so and just note that if we have this quadrant, say first quadrant, second quadrant, third quadrant, and fourth quadrant, right? So in the first quadrant, both so this is my real and my imaginary, right? Both will be positive. So we will be having cos theta plus j sine theta, right? Here we will be having minus cos theta plus j sine theta. Here we'll be having minus cos theta minus j sine theta, right? And we'll be having cos theta minus j sine theta, right? So is anyone having any confusion on this, the angular Euler notation? Does anyone have any doubts in this? All right, so we'll move ahead. So as we computed x0, so let us see what is x1 coming out to be, right? So what will be x1? So it will be again 1 by 4. Right. So you have x1 e to the power 0, right? This is at L is 0 and for k is 1, right? So we are going to compute for k is 1. So first what we'll do L0, then we'll take L1, L2 and L3, right? And we need to sum all these four terms together, right? Plus x2 e to the power j 2 pi. What is my k and L? For L is 1, it is 1, right? By 4 plus x3 e to the power j 2 pi. Now here we have L is 2, right? L is 2 and 2 into 1 is 2. So k into L is 2 divided by 4 plus x4 e to the power j 2 pi, and for L is 3, this is 3 by 4. Any doubts in this step to anyone? No doubts. Okay. So now I will substitute the values of x1, x2, x3 and x4 right in this. So we'll get 1 by 4 minus 1 right, and e to the power 0 is 1 plus 2j, and if you solve this you get e to the power j pi by 2, e to the power j pi, e to the power j 3 pi by 2, right? So these are the 4 phases which we are getting. Okay. And now we need to compute each of these phase as I discussed here. If anyone has any doubt in any step, just ask. Okay, feel free.
Can you
Yes.
explain this phases again?
Okay.
Yeah.
Which part? If you can.
This pi part,
The lower
pi
one.
part.
This one.
The above one.
The above one.
Yes.
Okay. Okay. Right. We'll just come back to this in a moment. So we have these two axes, right? So we have the x-axis and we have the y-axis. Okay, so this is say the y-axis. This is my x-axis. All right. Now the x-axis is my real axis. Okay, and the y-axis is my imaginary axis. Right. Now just remember the Euler's identity. What is Euler's identity? Let's not confuse. So Euler's identity is e to the power I theta is cos theta plus I times sin theta. Right? Is this clear? Is this step clear?
Yeah, got it now.
All right. So
Yeah.
what is this? This is my real part, right? Cos and I times sin theta, right? So this is my imaginary part, right? All right. So the x-axis or the real axis is having my cos, right? So my cos is my real axis and my imaginary axis will be having the sine component, right? So we have the cos component on the x-axis and the sine component on the y-axis, right? Now, right now for any angle, right? For any arbitrary theta, right? If we want to have, right? So at this axis, it will be cos theta plus I times sin theta, right? Now, if we have say theta is in the second quadrant, then what will happen? So now see my x is now minus x-axis, right? So this is the negative x-axis. So since it is negative x-axis, so we have minus cos theta plus I times sin theta, right? So if you see the sine is still in the positive axis, right? So this is the if I can use another color. Okay. So if you see this is the plus y-axis, right? Or the plus sine axis. Similarly, this is the plus x-axis, right? This is the minus y-axis and this is the minus x-axis. Is this clear up to here?
Yes, it's clear.
Right. So in the second quadrant, if we have any angle, it will be minus cos theta plus I sin theta, right? Similarly, if we have any angle in the third quadrant, what will happen? My x is negative, so it is minus cos theta. My y is also negative, so minus I sin theta, right? And if we have any angle on the fourth quadrant, right, then we have now my x is positive. Let's see, my x is positive, cos theta minus I sin theta, right? Is it clear?
Here we will use I and J interchangeably, na? Generally we use
Okay,
J.
okay. Is this the problem? All right. Yeah, yeah, yeah. So this is actually J. Yeah. So it is e to power j theta. So it is cos theta plus j sin theta. Right.
Okay.
Yeah. Was that the problem? So wherever you have this, just replace I with j. Okay. So
Yes.
yeah. So the problem is in electrical engineering, I represents the current. So that is why they use the uh, complex parameters are represented with J. Yeah.
Okay.
Yeah. Clear, right?
Yes.
Anyone else has this doubt? No? All right. So, right. So let me just solve this down. So for x1, it will be 1/4 minus 1 times 1. I'll just write it again. 2j e to the power j pi by 2 minus j e to the power j pi plus 3 times e to the power j 3 pi by 2. Right. So let's just solve this. So you have 1/4 minus 1 plus 2j. All right. Now what is e to the power j pi by 2? Right. So this is cos pi by 2 plus j times sin pi by 2. Right. Minus j cos pi plus j sin pi. Again, if anyone has any doubt at any step, feel free to stop me. Plus 3 times cos 3 pi by 2 plus j times sin 3 pi by 2. Any doubt in this step?
Not in this step, but if e raised to the power is negative, then also you will like problem.
We will come to that. When e
Oh,
is negative, I'll come. That is a DFT question. We will
oh,
take that when it comes. So
oh,
any problem in this step?
no.
Okay. Others can also intervene at any time. All right. So we'll again use this, and also you should just remember the values of sine and cos, right, at various degrees, right? So 0 degree, 30 degree, 45, and 90 degree. I hope you know these values, right? So sine is 0, 1/2, 1/√2, 1. I hope you just know this, right? And in cos, it gets reversed. So cos 0 is 1. And similarly, cos 90 is 0, right? Is anyone having any problems in this? Okay.
No, sir, no.
All right. And just one more thing. So in this, 4 quadrants which we have, 1, 2, 3, 4. So this is my 0 degree, right? 0 pi radian, and this is my pi radian, right? So this is pi by 2, and this right, and this is 3 pi by 2. Similarly, we have 4 pi by 2, which is 2 pi, right? 4 pi by 2. Then we have 5 pi by 2, then 6 pi by 2 is 3 pi, then 7 pi by 2, then 8 pi by 2 is 4 pi. So if you see that the sign will be 0 for all these, right? So sign will be 0 in 0, 2 pi, 4 pi, everything, right? Similarly, the sign will be 0 for this also, pi, 3 pi, right? So sign will be 0, right? It is understandable, right? At pi, 3 pi, 5 pi. So for all n pi, sign will be 0. Okay. So sign n pi is 0. N is 0, 1, so on. right? Similarly, the cosine will be 0 at these points, right? For the y-axis. So cos pi by 2 is 0, cos 5 pi by 2 is 0, cos 3 pi by 2 is 0, right? Okay. So if anyone still has any doubts in these angles, just refresh the trigonometry a little bit. Okay. And now we are just going to put in values, right? So what we were doing. So yeah, we were computing x of 1. Right? So x of 1 is finally coming out to be 1 by 4 minus 1 minus 2 plus j minus 3j, and this is 1 by 4 minus 3 minus 2j, and we have minus 3 by 4 minus j by 2. Right? This is my x of 1. Okay. Now similarly, what will be x of 2? Now at x of 2 we have k is 2. Right. Okay. Now how will x by x of 2 be written as? So it will be 1 by 4, again x0. This is at L is 0, right? And since it is L is 0, k into L is 0. Okay. Plus x of 1 e to the power j 2 pi, for L is 1. This is k into L is 2, right? K into L is 2 by 4 plus x of 2 e to the power j into 2 pi. Now my L is 2, so k into L is 4 divided by 4 plus x of 3 e to the power j 2 pi. L is 3, so 3 2s are 6 by 4. Is anyone having any doubt in this step? So, all right. So we are just expanding the general which we have, right? So summation L is 0 to 3 x of L e to the power j 2 pi kl by 4. We are just expanding this. And finally, we have for k is 3, right? X of 3, and this will be 1 by 4 x of 0. This is at L is 0. So since L is 0, so my exponent is 1, right? E to the power 0 is coming always, it will be 1. This will be 1 plus x of 1 e to the power j. Now at L is 1, what we have 2 pi, k into L is 3, right? So this is 3 pi by 4. Similarly, we have x of 2 e to the power j 2 pi. For L is 2, we have k into L is 6, right? So we have 6 by 4. Similarly, x3 e to the power j 2 pi. Now L is 3, so k into L is 9. Okay, 9 by 4. Any doubts in this? Okay. So you can just solve it at your own home. It is once you have written it in this step, then you just need to patiently solve these angles. That's all you have to do. Right. So I'll just write the answer. So we have x of 1, right, x of 0 is, we had in fact x of 0 we computed here, right? 1 by 4 plus j. Okay, x of 1 is minus 3 by 4 minus j by 2. X of 2 is minus 1, and x of 3, minus 1 minus 3j by 4, and you have 1 by 4 plus j. Okay, this is your time domain. And so if you just write them in a block, x0, x1, x2, x3, right? So this is for block, but note that you need to now add cyclic prefix to this block, right? So my x3 now comes, hey, we have a cyclic prefix of 1 for L is 2, right? So now this is my block, what it is going to be. So what was asked in the question, if you this happened. Can you see the question screen clearly?
Yes.
Okay. So if we see this, so the answer is coming out to be the first one, right? So see this x3 is 1 by 4 plus j, right? So it is also ending with 1 by 4 plus j, right? So my A is the correct answer. Okay, let's move ahead. Question 4. Okay. So question 4 is also following question 3. And here we need to, the received symbols across the subcarriers. So, all right. So we are given in time domain that y0 is j, y1 is -2, y2 is 4, and y3 is -2j. Okay, we are given. So this is in time domain. Okay. Now we need to compute in frequency domain. So how do we do that? So y of L is summation k is 0 to n minus 1 yk e to the power minus j 2 pi kl by n. So this is the general formula of DFT, discrete Fourier transform. So now we need to solve this. Okay, so let's do for y of 0. So at L is 0, we have y0, capital Y0. What will this be? So this will be y of 0. First k is 0, right? Since k is 0, so the exponential will be 1, right? E to the power minus j 2 pi 0 by 4, right? So this is 1. Okay, plus pi of 1. Now if k is 1, but note that L is still 0, right? L is still 0. So this is still e to the power minus j 2 pi 0 by 4, right? So this is still 1. And plus y2 at k is 2, and e to the power is still 0, plus y3 at at k is 3, and e to the power 0. Any doubt in this step? Any doubt to anybody? Doubts? Okay. So y of 0 will be a simple summation of all the 4 y's which we have. And if we do that, we have j minus 2 plus 4 minus 2j, and this is minus j plus 2. Now let us solve for y of 1. So it will be a bit complicated. Y of 1. So again, this will be y of 0. So what is y of 1? At L is 1, right? Y of 1 means at L is 1. So first we will expand for k is 0. So e to the power, was my formula. So we have minus j 2 pi k times L is 0 divided by 4 plus y of 1 e to the power minus j 2 pi. Now k is 1 for the second term, right? For the second term k is 1. So k times L is 1 by 4 plus y of 2 e to the power minus j 2 pi. Now k is 2 and k times L is again 2 by 4 plus y of 3 e to the power minus j 2 pi, k is 3 and k times L is 3 by 4. Any doubt in this step? Anybody? No doubts? So now we are going to, substitute the values. Let's substitute values later. First, let us expand the exponentials. Okay, so we have y of 0 and e to the power 0 is 1. All right, straightforward. Plus y of 1. Now what do we have? So this is pi by 2. So this is cos pi by 2 minus j sine pi by 2. So just remember this identity that if you have e to the power minus j theta, then it is cos theta minus j sine theta.
Cos theta would not be negative.
No, cos theta won't be negative.
Okay.
Right. No doubts, right? So I'll go ahead. So we have y1, then we have y2. For y2, what do we have? So this is cos pi minus j sine pi. And finally, we have y3 cos 3 pi by 2 minus j sine 3 pi by 2. Anyone is having any doubt? Feel free again.
One basic doubt. Uh, this like y3. So all y components are following this e minus j theta is equal to cos theta minus j sine theta. Then only minus j, it is like angle always remain positive. It does not, it is never negative. Theta.
No. Theta can be negative, right? So we have, if you remember this, right? So here theta is positive in the first quadrant. I mean, okay. I mean, yeah, theta is always positive. You can say that. Fine.
Okay.
So
Yeah, I
what
got.
is your point?
No, I got it. Like we have already taken the negative outside. It is like plus j or minus j, or so then only you will compute. Like sine value will give, sine of angle will give whether it is positive or negative. We know that 0 to 90 it would be positive, and
Right.
then it would be, yeah, got it.
Yeah. So if anyone ever feels problem, just draw this 4 quadrant. You will understand what is happening. So yeah. Right. So just remember minus of theta is, if you see with respect to the this axis, right? So this is minus of theta, right? So if you are moving in the reverse direction, then it is
Okay.
negative of theta.
Yes.
Yeah. So if you see it from one sense, you have theta, right? And what is this? So it is
Pi minus
kind of, yeah, it is kind of complementary, right?
pi
So
minus theta.
right. So that is what is happening. Yeah.
Got it. Yes.
Okay. So what will, let's just solve this. So we have so for y of 1, right? So no other doubts in this, right? How we are expanding this, and this will come out to be minus 2 plus 3j. Okay. So similarly, y of 2 will be 6 plus 3j, and y of 3 will be minus 6 minus j. So does anyone want me to do for any other y, or you can just go back and see the video, right? If you feel doubt in the concept. So what we have is that yeah, and y of 0 was 2 minus j. So if you just look into the options which we have, then option B is, matching the answer. Okay, let's move ahead. Question 5. So this is also following the previous two questions, and it has asked that the estimate of channel coefficient across L is 3. So it has basically asked what is h hat of 3, and for OFDM we know it is y3 over x of 3, right? And this is all in frequency domain. Just remember that this is all in frequency domain. So if you do, and what is y of 3? So y of 3 we solved earlier, it is minus 6 minus j, and x of 3 is directly 3. That this is given in question itself. This is given in question. This we solved in the previous question. Okay, so what is my h hat of 3? So it is minus 6 minus j divided by 3, and this is minus 2 minus j by 3. So minus 2 minus j by 3 is option B. Any doubts? Any doubts? No, right? Right. Question 6. So question 6, it is again following the previous, the variance of the estimate of channel coefficient. All right. So what to do? So now we are given that sigma square is minus 3 dB, and note that this is over one subcarrier. Okay, this is over one subcarrier. So 10 log 10 sigma square is minus 3 dB. So sigma square in watt will be approximately half. So I was seeing in the forum that people have replied that NPTEL provides this virtual calculator when you will be giving exams. So in last class, someone had asked that is calculator allowed? So yes, virtual calculator is present. So you can just compute sigma square is coming out to be half. Okay. So note that this is sigma square over one subcarrier. So the noise over all subcarriers, right? This will be n times sigma square. So this is 4 times half, which is 2. Okay. Now, if you see h hat L is y of L over x of L. What is y of L? It is x of L, h of L plus v of L divided by x of L. So this is h of L plus v of L over x of L. And what is this, right? So what do we have? H hat L minus h of L is v of L over x of L. If anyone has any question, just you can intervene. So if you see, this is my error, right? This is my error, and therefore the expectation of h hat L minus HL squared will be the expectation of v of L over x of L squared. And this is basically, n sigma square divided by x of L squared. So this is 2 n sigma square, and this is 3 square, which is 9. So we have 2 by 9. Any doubts? Okay. Question 7. So, okay, in this question, it has asked the estimate of channel types H0 and H1, how they are, given. So just remember the 4 equations which were there, right? So if you just use those 4 equations, we have H of 2, H3, and this will be 1 minus 1, 1 J, H0, H1. So what you will have is H hat 0, H hat 1 will be the inverse of this matrix, right? 1 minus 1, 1 J inverse H hat 2 and H hat 3. So just you can look in the class the 4 equations, and you need to solve those 4 equations, and you will be getting this matrix, and you just need to invert that matrix, and so the answer is C. Okay. Question 8. Okay. So in question 8, what is it given? All right. So this is again similar to question 3. So the problem is similar to question 3. And what we are given in frequency domain, this is -2 plus 3j. This is -1 minus 2j. Similarly, x of 2 is 2 plus 2j, and x of 3 is -2. Right? We are given this. So now what we are asked, so transmitted block in time domain, right? So we are asked x3, x0, x1, x2, x3, right? So this is the block which we are transmitting, and this is my cyclic prefix, right? So what do we need to apply? We will be again, applying the IDFT. So apply IDFT. What is IDFT? So x of k is 1 by 4 summation L is 0 to 3 x of L e to the power j 2 pi kl by 4. So I'll not, I'll not solve this again. So you can do it at your home, and I'll just give you the answer. You can just cross check it. So we get x of 0 is -3 by 4 plus 3j by 4. X of 1 is -half plus j by 2. X of 2 is 3 by 4 plus 7j by 4. And x of 3 is -3 by 2. Okay. And the answer is A. So this is, if you see -3 by 2, it is starting from -3 by 2, it's ending in -3 by 2, right? And we have the x0, x1, x2 in the middle, right? Question 9. The symbols received across subcarriers in frequency domain. So now again, this is similar to question 4. So let's just write this. So you have y0 is -j, y1 is -2 minus j, y2 is 3 plus 2j, y3 is 1 plus j, and these are in time domain, right? These are in time domain, and you need to convert them into frequency domain. And how will you do that? So you will be using the DFT, right? That is y of L is summation k is 0 to n minus 1, which is 3 by k e to minus j 2 pi KL by, right? So again, I just write the answer. So we have y of 0 is 2 plus j, y of 1 is minus 5, y of 2 is 4 plus j, and y of 3 is minus 1 minus 6j. Okay, and the answer is C, option C. The final question. So they have asked the estimate the coefficient h1, right? So that is h hat 1 is basically y1 over x1, right? Directly, and y of 1 is minus 5. And x of 1 is minus 1 minus 2j. So you will get this in solving question 9, and this you will get from question 8. And how will you solve this, right? So you need to factorize it. So I hope you know how to factorize it, right? So minus 5 minus 1 plus 2j, you will multiply and divide on both sides. Minus 1 plus 2j, and then you will, so this will be of the form a plus b, a minus b. So this is, a plus b, a minus b, which is a square minus b square. And you will be solving it, and you will be getting 1 minus 2j. Any doubts to anybody? Any other thing you want to discuss? So I think, yeah, Manish has something to say. Go ahead, Manish.
No, sir, no doubt, sir.
All right, all
No
right.
doubt.
Okay. I think we have had an extended class today, so okay, no problem. So okay, and I'll stop the recording. Right. Thanks.
Thank you, sir. Thank you.